My name is Akmal Shaik. I'm coming to you guys from here in Cumberland, Rhode Island. A quaint town, but it's a lot of things a happy town. Um, Wait, hold up. Sorry about that. Let me make it so.
We can see your screen.
Yep, it's just kind of in the way of my screen. That's why I'm trying to fix it.
No worries.
There you go. That's pretty good. All right. So today I'll be presenting about pulsars and how they contribute to the interstellar GPS. All right, so first things first, what is a pulsar? Well, a pulsar is a neutron star. A neutron star is in its most basic right, a corpse of a cold dead corpse of a massive star about 20 to 30 times the mass of our sun. And so what happens is whenever these stars run out of their nuclear energy, which is like hydrogen and helium, they have no more means of making energy, and they go through what is called a core collapse supernova. As you can see in the picture down here, what happens is that the core of this star, which is like right in the center, it collapses in on itself and becomes this really small ball, while the rest of it is exploded at really fast speeds into space. And so what's left is a neutron star with a mass of about 1.4 to 3 times the mass of our sun, which is one solar mass being the mass of our sun, as is written over here, into a ball that's only about 10 kilometers across, which is barely bigger than the city of Manhattan in New York. And because of both of the mass and the radius, what you have is an object with a gravity that's insanely high, which is 200 billion times that of Earth's. And the key takeaways from this is that one, it has immense density because it's so small and so massive. And two, it's because of the conservation of angular momentum, you end up with an object that it has extremely high rotation speed, which means these pulsars can rotate from either 100 to even 700 times a second, which is insane. Um, and then the third key takeaway is that, sorry, it's can't read it because it's out of the way. It has a extremely powerful magnetic fields, which is going to be extremely, which is going to be important when you're talking about what makes a pulsar pulse. All right, so the difference between a neutron star and a pulsar is that pulsars pulse. And the reason they pulse, or the reason there's light emitted from these guys is because here at the magnetic axis you have radio emission as it says on the screen. Well, the picture says radio emission, but in reality is just light energy being emitted from each of the axes of the magnetic axes. And the difference and the big thing here to know is that the magnetic axis is different from the actual rotational axis, which is right in the middle of the diagram here. And this axis misalignment creates what's called the lighthouse effect. What is the lighthouse effect? Well, just as a lighthouse shines its beams across the sea, the pulsar's misalignment causes the actual or the axis misalignment causes the beams of light to sweep across all of space. And so you have this kind of big lighthouse effect happening when talking about pulsars. And let me just pause this real quick. So what you actually do see when you're looking from Earth is the only thing you see is when the lights of the beams of light actually pass across us, it just makes the pulsar grow brighter. And the rest of the sweeping effect you don't see. So you just see this kind of pulsating effect you see down here. In terms of universe's timekeepers, they are extremely stable and they even rival the accuracy of atomic clocks, which are man-made clocks that are extremely accurate. All right, so data measurement analysis. The important thing to know with pulsar is that they all pulse in different areas of the spectrograph. As you can see in the top right graph over here, you have gamma rays, you have X-rays, ultraviolet rays, visible light, and radar, radar and radio waves, which are the big ones that pulsars pulsate in, or the emissions of pulsars are in those areas or those types of emissions. And as you can see in the little GIF in the corner, in the bottom left corner over here, when the actual beams of light pass across us, we have this big peak in light intensity, which directly corresponds to these kind of graphs over here. Now, the reason that there's a smaller peak is because even when a pulsar beam passes near us, we still detect some of the light waves that come from the pulsar, and so you have this kind of little peak when it comes past us, and the big peak when it actually goes over us. All right, so what is XNAV and why is all this important? All right, so to understand XNAV, we need to understand what GPS is, because they are extremely similar and hence always used. And GPS is always used to describe what XNAV is. So take your phone, for example. You have your phone on you and you're trying to figure out your position. What happens is your phone and the GPS detectors inside your phone, they pick up these signals that are sent from at least 4 of the satellites that are orbiting Earth at extremely fast speeds. And so what you have is these satellites always emitting these signals to your phone, which it then picks up. And the key here is that your phone analyzes the time it gets a signal, and within the signal, sorry, I should have said this earlier, but the satellites in their emissions, they also tell you when or at what time the signal was emitted from. And so your phone takes both those information and it analyzes the difference in time between it being sent and it getting here, and multiplying that by the speed of light to get the actual distance from us to the satellite. And when you have 4 of these, you can finally figure out where you are. Now, the only differences are kind of 3 main differences between GPS and XNAV, is that with XNAV, we don't have man-made satellites spread out across the universe. So now we have to use these things called pulsars, which, as we said earlier, they are 1, super stable. 2, they're extremely precise and accurate in terms of timekeeping. 3, they emit signals extremely quickly. And 4, there are abundance of it. So we have a lot of diversity in what kind of pulsars, in terms of their noise, like the noise around them, or how fast they emit, how bright they are. We can use which pulsars we want for XNAV. All right, and the second main difference is that, sorry, I don't have note cards, so I have to use a notebook. But the second difference is that pulsars don't tell us when they sent the pulse. And so the way we go around that is we have these things called pulsar ephemerides and databases, which have predictions of when pulsars have emitted their lights and when they should be coming. And all of that is then put together to figure out, to do the same calculation that were done in GPS in XNAV. And the third difference is that instead of needing to have 4 satellites to figure out our location on Earth in space, you only need 3. And the reason for that is because you already have a prediction of where the satellite should be, and so all you need is the three pieces of evidence to kind of prove that. All right. So XNAV, and to do this, it requires 3 things. It requires 1, an X-ray detector to actually pick up the emissions from all these pulsars. 2, it requires a pulsar database and ephemerides. It needs to have that in its own system. And 3, it needs an analysis software system, which is the thing that does all the analysis of both, or basically does all the comparisons between both what our predictions is and what we're actually looking at to figure out where we are. All right, so we're getting to actual experiment here. So NICER and Sextant. These are both placed on the ISS, and NICER is a science mission that was already placed on the ISS, which is the Neutron Star Interior Composition Explorer. And so the main objective of NICER, being a science mission, is that it's there for the sole reason of studying neutron stars and, I guess, their composition. The way it does this, of course, is by detecting X-rays and doing a little bit of preliminary analysis already within its system before sending that to scientists on Earth to do the analysis. The 2 things it does is it does noise filtering and it does pulse phase processing. Noise filtering is basically figuring out of the data of the vast amount of data that you pick up, which ones are actually important and which ones are actually from the pulsars itself, as opposed to just any other thing inside space. And two, it does a pulse phase processing, which basically means that it makes those the graphs we saw earlier with the little peak and the big peak, it puts all that onto a graph with time, and it does all that before it sends the data to Earth. All right, which is extremely important for a bit. I'll tell you in a bit. So Sextant is the station experiment for X-ray timing and navigation technology. So what Sextant is what's called a tech demonstration, which means it's an experiment to prove that a concept can work. And the concept in this case is X-ray navigation, or XNAV. So what Sextant actually houses in its software is it houses one, communication to and from Earth, and two, it also houses the analysis, or the things to do the analysis, which is to find the position of the actual spacecraft. All right, so the objectives and experiments in the Sextant mission of like late 2017, early 2018 was NE number 1 and NE number 2. NE number 1, or NICER experiment number 1, is observing 3 to 5 pulsars for approximately 2 weeks to find out that your predictions of where the ISS is within 10 kilometers of where the ISS actually is. So there's only like a less than 10 kilometers difference between your prediction and reality. And the difference between NE1 and NE2 is that NE1 uses data from both NICER, and it correlates the data from radio telescopes on Earth. And NE number 2, or NICER experiment number 2, is only using data from NICER, and its main goal is to test the self-reliance of the system. All right, so the results and conclusions of NE number 1 is the graph you can see on the left. The big thing here is that this graph is completely is basically not changed from what we actually have, what was actually detected during the time of experiments. And so the results here is that, as you can see, like in the green line, which is the nav error with measurements, which is the results of the actual analysis, you can see that just within 8 hours, it was below the KPP. The KPP being the key performance parameter, which is what says that it needs to be under 10 kilometers worst direction. And so the conclusion is that NICER is on a pretty good path in terms of being successful with using data from Earth to kind of support that. And so here's NE number 2. So the objective here, of course, was using only NICER data. And you also see that even though this was like around like 6 to 8 months after NE number 1, that was in November, this is in July, so yeah, around 8 months, sorry. You can see that just within 8 hours, it once again was able to stay beneath the simplified KPP, which is like around 17.3 kilometers. And the reason it's not 10 kilometers and it's 17 kilometers is because it accounts for other errors outside of Sextant. So like precision errors or timing errors, or some other stuff going wrong. And so the conclusion here is that NICER is on its way to being extremely self-reliant, and the only reason it isn't right now is because it doesn't have enough data by itself to be conducting these experiments, to be as successful as it was with data from that we've discovered on Earth for years to come. So the main thing is that with more time, you get better accuracy. Thank you. That's my presentation, and I will be taking questions now.
Amazing. Thank you so much, Akmal. Please put any questions in the Q&A. I actually have some that I would be very curious about. So I know very little about stars. Let me just say that. I'm curious. So you mentioned that pulsars and neutron stars are when sort of the star collapses on itself. I've kind of heard elsewhere that that's also how black holes are formed. And so can you explain how and why the pulsars are stable and why they just don't turn into black holes?
All right, so the reason that pulsars stay their size instead of, oh my God, did it again. Sorry, I'm just trying to get back to the last page. Thank you page. So the reason that pulsars don't collapse into black holes is
Mhm.
because of this thing called neutron degeneracy pressure, and that basically states that once you get to the point where neutrons where it's the pressure is so high that atoms basically convert into just neutrons and kind of split off from their electrons and protons. Once you get to that point, you can't collapse anymore unless it passes another I don't know how to explain it, but the reason black holes collapse on themselves and go past the degeneracy pressure kind of parameter is because black holes are just that much more massive that the gravity kind of overtakes this principle and it collapses in on itself. Pulsars and neutron stars don't do that yet. They don't have enough to do that.
Cool. So they're too skinny to do that.
Yeah, they don't. Yeah.
Cool. We have a question from Sanvi actually. So how can pulsars be used for spacecraft navigation in deep space? And what are the advantages of using them over traditional navigation methods?
Okay. So right now, a lot of navigation when it came to crewed missions like to the moon, those were highly dependent on being able to talk back with Earth and to kind of have Earth say, "Yay, we're here. How far are you?" The reason that's not good for deep space travel is because you get to a point where communicating with Earth is extremely unproductive. It's hard to get these signals to go that for that long, that far into space, and being able to sustain that is extremely difficult. When it comes to XNAV, and the reason a lot of scientists have been working on this for so long is because the self-reliancy that comes with XNAV is what looks really promising. If we're able to have a spacecraft using Sextant or XNAV by itself, we don't need to talk with Earth or communicate with Earth to figure out where in space we are, and that'll not only allow for uh, crewed missions to just to Mars, but even past our solar system and into the interstellar space.